In the 5th chapter, we will introduce the knowledge of homomorphic analysis, HA. What is the problem of deconvolution? What is the homomorphic system? How to use homomorphic filter to do the speech signal analysis. Also, we will know the concept of spectrum through homomorphic transformation. Firstly, we will have a brief review of general discrete time model of speech production. The short segment of speech can be modeled as having been generated by exciting an LTI, linear time invariant system, either by a quasi-periodic impulse stream or a random noise signal. As we can see from the scheme of speech production model, the voice speech sequence PLN can be generated by the convolution of the input sequence Pn and the impulse response HVN. And voice signal can be generated by the convolution of the input sequence UN and the impulse response HUN. Considering the basic speech model, speech analysis aims to estimate parameters of the speech model, to measure their variations and perhaps even their statistical variabilities for quantization. With time, speech can be regarded as the convolution of excitation and system response. How to deconvolve speech into excitation and system response? There are two kinds of deconvolution methods. One method is to build a model for the linear system and to express the system with model parameters. This method is called parametric deconvolution. Linear predictive analysis belongs to this kind of method. Another method is non-parametric deconvolution. We could do this using homomorphic filtering methods without a linear system model. Homomorphic filtering is a nonlinear filtering that obeys the generalized superposition principle. It is possible to separate non-additive combined signals, such as multiplicative or convolutional combination. In mathematics, deconvolution is an algorithm-based process used to reverse the effects of convolution on recorded data. The concept of deconvolution is widely used in the techniques of speech signal processing and image processing. For example, the figure shows signal x1n and x2n with disjoint low and high frequency spectra s1 omega and s2 omega. By designing a deconvolution algorithm, the input signal xn with convolutional combination in time domain can be converted into the additive combination in frequency domain. Furthermore, through the proper system h omega, we can get the necessary signal x2 omega in frequency domain. In physics and systems theory, the superposition principle, also known as superposition property, states that for all linear systems, the net response at a given place and time caused by two or more stimuli is the sum of the responses which have been caused by each stimulus individually. So that if input x1n produces response Ls1n and input s2n produce response LS2n, then input x1n plus x2n produces response LX1n plus LS2n. The homogeneity and additivity properties together are called the superposition principles. A linear function is one that satisfies the properties of superposition. It is defined as shown in the equations. This principle has many applications in physics and engineering because many physical systems can be modeled as linear systems. Linear systems are defined by the principle of superposition. A homomorphic system is a type of nonlinear filter, which is defined by the generalized superposition principle. The superposition principle is just a special case of the generalized superposition principle. Homomorphic systems are classified by operations in their input and output vector spaces. The input and output operation symbols can be inconsistent. Linear system is a special case of homomorphic system. That is to say, this system obeys a law similar to the superposition theory for input operation and output operation. Because it is a nonlinear system and promotes the application of the superposition theorem of linear system operations, so it is called a nonlinear system subject to the generalized superposition theorem. That is a homomorphic system or generalized linear system. Convolutional homomorphic system or homomorphic system for convolution refers to a homomorphic system in which the input signal combination and the output signal combination are both convolution operations and obey the generalized superposition theorem. As homomorphic system can be represented as a cascade of three systems. The character system D with operation symbol circle takes input signal x1n and x2n by use of the rules of operation circle and transforms them into general linear combination D circle x1n and D circle x2n. Since the system D circle is determined by the operation circle, it is called the characteristic system of operation circle. The second system L is a general linear system, which determines the characteristics of homomorphic system and is the focus of system design. The third system transforms addition operation to triangle operation. The system D triangle is determined by the operation triangle and is called the characteristic system of the operation triangle. As to the convolutional homomorphic system, the input operation symbol circle and the output operation symbol triangle are both convolution operation. The system takes inputs combined by convolution and transforms them into additive outputs, then pass through a conventional linear system. Finally, the inverse of first system takes additive inputs and transforms them into convolutional outputs. The first system is fixed and called the characteristic system for homomorphic deconvolution. The second system is a linear system and important in designing. The third system is fixed and called the characteristic system for inverse homomorphic deconvolution. We can get the canonic form for deconvolution using DTFT. The first problem is to find a system that converts convolution to addition. Convolution operation is a multiplication form in the frequency domain. After the process with DTFT, we could use the logarithmic function to convert products to sums. Thus, in frequency domain, homomorphic system makes multiplicative operation into linear additive operation. For discrete time domain, we could use Z transform to build up the homomorphic system for convolution. As is shown in the figure, A is canonical formulation of convolutional homomorphic system. B is the subsystem deconvolution. C is its inverse. The characteristic system deconvolution contains three parts to convert convolution into additive with Z transform and logarithmic function. The inverse system converts additive back to convolution with Z transform and exponential function. That's all for this session. See you next session.